So this video is my latest circuit, and the circuit has to do with parametric excitations. That's the term that Eric Dollard has given to this circuit. So what you do is you take this capacitor here and you right click it to edit it, and then I like to put in a lowercase y, click apply, and then erase the y and click apply again, then put in another y and click apply, and then backspace and click apply and put it back in again, and then take it out. Whoops. And then, oh, no wonder I have the wrong. Oh, this is the realistic simulator. This is not the equivalent series simulator. How about that? Accidentally started in a different simulator. And I just keep doing this over and over again. Seems boring, but you'll see in a second. You see, there are some changes down below if you watch what the result is down below. But I just keep doing this. Yeah, it takes a little longer in this with equivalent series resistance, which kind of makes sense because this is supposed to be more of a reality check, you know, real world kind of thing. Sorry. Oh boy. That's what happens when you get old, huh? Alright, so click that and go down again. So I'm going down to Yocto. That's a scientific notation that's 10 to the negative power of 24. So that's 24 places to the right of the decimal place. That's a lot of... But I want to speed things up and ensure that I get results. I could do millifarads, which I usually reserve for the very end when I'm nearing my target. Oh, wait a minute. It stopped improving. Oh, there it goes. Basically, when I reduce the farads on this capacitor, the voltage goes up. And when I go back, see the voltage precipitously rose. Now when I go back up to 10 farads, the amperage goes up and the voltage goes down. So it's like taking turns. Now I'm getting noticeable results. So I'm not going to use Yocto. I'm going to use milli, lowercase m. So the amperage went up and the voltage went down. No, excuse me, the voltage went up and the amperage went down. I wasn't paying attention, sorry. So now the amperage goes up and the voltage goes down. Let's do that again. So the amperage should go down, yes, and the voltage goes up. And basically, you don't come out even Steven after a cycle of, after you pass through two of these phases, two of these half phases. You do gain. Now, once in a while, there is, statistically speaking, there is the possibility that you actually lose rather than gain. Lose, different than what you would normally gain. In which case, that overall the wattage does not gain. But that's rare. Most of the time, you gain. Let's see if this is too much. No, it's still pretty good. So equivalent series resistance does put reality into this, and then I don't have to worry about overshooting, because that was my problem in the other regular simulator of Paul Falstad, is overshooting, and then it makes it problematic. And plus it takes longer this way, so you can't overshoot because it takes longer as well. Both is true. I think this is a very cool circuit because it defies convention, for one thing. I love defying convention. I live for that. And it's definitely is free something. Well, it is free electricity. You know, I used to think I would, well, because I had the battery capacitor battery sandwich. Now I don't use that. So I'm actually gaining in both departments. So this is truly electrical, um, what do you call it? Synthesis. Just as Eric Dollard says it is. So I was wrong. And he's right. But I modified it such that you don't have to synthesize both components of electricity. By and large, you know, there's nothing absolute about this. But by and large, you can focus just on one factor or another. And I was focusing on the amplification or the synthesis of current. For the most part, far excessive or exceeding that of voltage. But now I'm doing both. But the problem with this here, because there's no battery, capacitor, battery sandwich regulating this, that there's actually a few benefits. One is you don't have to carry around a battery pack in your car, in your electric car. The other is that, or the caveat that goes with that is that you have to be fast when after you've gone downwards, to quickly go back upwards, because here right now everything is stable. Okay, but when I go down, the voltage doesn't merely increase, it escalates, or at least it did once before. I don't know why it's not doing that now. Oh, because I'm in equivalent series resistance simulator. Yeah, when I'm in the normal Paul Fawcett simulator, it was a problem because the voltage actually didn't just rise while the amperage fell. It actually escalated and kept escalating and would have gone to infinity, and that means the impedance, there was a lot of impedance. So for some reason, having equivalent series resistance built into the caps and coils helps eliminate some of that impedance. Isn't that the most strangest thing? Because look at it, all these lines are even. Now, except for the wattage on the AC source. But I don't have to worry about how quickly can I do this. So I could do this manually. I wouldn't have to have a car computer do it for me. How about that? So we're slowly, so I like this version better. Too bad I didn't tie this to the realistic simulator, because this is more realistic. Electrical paradox, I can't, yeah, I can't redo that. I would have to get a whole nother shortcut. Well, if I can think of a new name, as I gradually increase here. Although the volt still exceeds, oh, that was the other thing. I think the other way, I had some control. Maybe not, because here the voltage, yeah. Maybe I did, I don't know. So we just keep going, because I haven't reached my target yet. So we're up to 10 amps and 33 volts on the coil, or coils. They're all the same, so I only scope one. So 10 amps, 33 volts. Oh wow, that's a lot of volts, but that'll come down. So the system has to accommodate high voltage, because higher voltage and higher amperage than whatever target you're shooting for. So now I got 90 amps, which means I'm going to have a lot of volts. 285. Yeah, that is a lot. So, you know, normally for accelerating a car, you might run it at 200 amps, and cruising might be 50. So this is a little excessive for cruising, so this is like slightly speeding up in traffic. But let's try reducing less now. I like to do 100 milli when I go down. Oh, but it still was a big change. Oh no, the voltage dropped. No, it went up. Oh yeah, it did. My mistake. Oh, well, I'll come up to just 1 farad. How's that? Oh, I dropped. I have less amps now. Ooh. Oh my god, the voltage is huge. That was not a good idea. Let's try going up a little higher. See, yeah, if you overshoot, you can go to whatever value you want to go to. So I could go to 100, and my amps will still go up, and my volts will still go down. Oh, how nice. Look at that. So let's try 150. Not much improvement there. Yeah, that's, I don't know. Let's try 200. Well, at the expense of having a lot of capacitance. Actually, that's not bad. That's very close to what Greg Tuntlin wanted me to deliver. A circuit that would deliver. So it is possible. You know, all of this could be programmed into a computer, the car's computer. So that's pretty close. I think I'm going to stick with that. And I'm going to take a snapshot of this to make a picture out of it. So that's pretty good. And let's see, let's make a picture. A screenshot picture. So I can make something out of that. So, oh, and I could try saving this to make a precharged condition. And see how that turns out. Alright, let's load that one and see what happens. Whoops, what happened to it? It disappeared? Where'd it go? It went somewhere. Oh, I wasn't paying attention. It went in the wrong place. Okay. Enchanté. It needs to be here. Alright. Now I can go get it. Oh, that's pretty close. Look at that. So there's your there's a precharged one. Good, I'll upload this. Now the capacitor dropped, it looks like, than what it was. Oh, wow, yeah, the volts severely dropped, my God. But the amps are still high. So this is very much an amps-oriented circuit. Now the wattage is milliwatts. It's still kind of high. I didn't want to go with a lower capacitor, not that it wouldn't help. It would actually help protect the environment from radio interference and the wrath of the FCC. But if I'm only putting out 100 milliwatts, that's probably okay. You know, in terms of short range, it would disturb people, their radios, but not over a great distance. So that's still pretty good. Obviously, if a car manufacturer wanted to go to some sort of trouble, they'd want to reduce that further. So let's try that. Let's make it a femto and see what happens. If you ever wonder why it says this, series resistance cannot be exported, it's because I didn't want to go to the trouble of trying to figure out to take the software code to the next level. Oh, no, it was more than that. It was not expedient for me to do so. It's more efficient for me not to do that. So you can temporarily, in the course of running a particular circuit, change the series resistance of your capacitors to some other value other than the default value of 10 milliohms. But you cannot save that value. That's the thing. While inductors, coils, they have a preset mechanism in which the series resistance the equivalent series resistance that the software that I made it do, put it in, it always puts it in a value of 4 times greater than whatever the inductance is. I just picked an arbitrary value of 4, a factor of 4. So you don't get to monkey with that, let alone save it. Sometimes you have to juggle, convenience or expediency along with purity or freedom. I'll have to remember that next time I don't like my lack of freedom. Okay, so let's see what happens now. Nothing. Absolutely nothing. So let's take it up to 10. Nothing happens. Oh yeah, I forgot about that. No, so it's a good thing to tell you. It doesn't matter what value you have here. Well, then why do I keep it at the low value? Maybe it has to do with changing. Well, let's lower this to 1. Yeah, maybe that was it. It's when you're changing this thing, it might matter. Maybe. I don't know. Oh, look at the power gain. Now the volts exceeds the amps. 1.5 kilovolts versus 500 amps, 3 to 1. So that's no good. So it pays to have the capacitors at a lower value when you're doing the up and down changing, the parametric variation of this capacitor's value. It pays to have this way, way, way down. Yeah, when you're running the thing, you know, like at this point, running it down basically, which is very slow. This is 1 second time frame, and so you can sit here and wait, and this is already 2 megaseconds, and you know you can sit and wait for this thing to lose its energy, but it takes a long time. Probably because there's so many coils here storing energy. Each one of these coils of 2 henries has a lot of storage in there because of that 2 henry value, and they're all in parallel, which may have something to do with something. I'm not sure what. And of course the capacitor and the transformer, you know, everything. Yeah, everything except the aerial stores energy, and the wire and the aerial, the antenna. Everything else stores energy. The transformer coils, the capacitors, the 3 capacitors, and the 12 inductors. The 2 transformer coils and the 12 inductors. So we got 14 coils here, although these 12 are air core in the way they've been constructed by Paul Falstad, while of course these 2 coils are iron core. Let's see, what else can I cover? So I was thinking I should have a new name and have it go to the realistic simulator. This is my desktop version. You can go to, you know, my website and get, you know, download the circuits, download the various simulators. Well, I guess I have nothing more to say. It's very interesting. And I don't know, I guess that's it. It's utter simplicity. You know, the circuit has so few moving parts, and it hinges all on a low coefficient, a coupling coefficient for the between the 2 coils of the transformer. I don't know how you construct something like that. I don't have the vaguest clue. I haven't bothered to look it up yet because I've been too busy making videos and making circuit simulations, crafting them. But you can go up to as high as 10%, you know. Normally default is 0.999. A motor, the relationship between the rotor coils and the stator coils is usually 0.5. So I chose to start off with 0.5, and then I was curious. I went down to, I went down to 10% from the 50, and that was an improvement. And then I tried going back up to 99.9%, and that was horrible. This way, when there's very little coupling coefficients between the primary and the secondary coils of a transformer, in this particular circuit situation, all of the energy lumps over here on the right-hand side where I want it, where the load is. Not out here to anger the FCC by the aerial. But if you have a strong coupling, that's where most of the energy is going to end up, and you're not going to get the benefit, and the FCC will come knocking at your door and take everything, including your toothbrush, because they do not like people disturbing radio interference in their local environment. So it's very crucial to have that awareness whenever designing circuits that have aerials. Now people have complained, well, gee, aren't you, you're going to be attracting lightning. Maybe so. Maybe so. But I think the lightning will be confused because I have 2 aerials now. Aha. See, in the past I always had 1 aerial, but now I have 2. and I'm only scoping the top one, but still I have two, and they take turns in terms of opposite polarity at any given moment, because these are this entire circuit is an AC oriented circuit. The only thing about the difference is it's not purely an AC circuit, it's a beat frequency AC circuit. So all these coils, all the components, everything is being subjected to a beat frequency of multiple sine waves. I don't know what effect that has on a motor coil. You know, it may create vibration and wear and tear due to vibrations, so maybe that's not so good. So maybe you got to add in, if you're an audiophile electronics expert, you could add in stuff to filter the input from these aerials so that it's a nice, clean, crisp singularity of a sine wave and doesn't have any beat frequency of complex sine wave, composition of multiple sine waves to create a beat frequency situation. What else? Yeah, so I choose to go down to 1 milli, or I think that's called 1 milli, 1 part per thousand, 1/10 of 1%, because that helps reduce my influence, my impact on my local environment, namely what happens at the aerial. And then putting capacitors in here, replacing what I used to have were resistors, is a big improvement. Because with resistors, even if I get the resistor very high, there's still a surge in the beginning when the circuit comes on, and that surge makes quite an impression on the environment, or some impression. And I'm trying to go for no impression, and then it quickly lowers. It lowers actually lower than what this is. Yeah, I'll show you what that does. If I take this out, and then we put in a resistor, and then we, I won't do anything fancy. Well, I will do something fancy here. Why don't I take this up to 100? Because 100 mega ohms is not too exotic. Maybe for high voltage it is, I don't know, but these situations. But, ooh, that looks good. That looks really good. So maybe what needs to happen is that the circuit has to be started up with capacitors here to prevent a surge from exiting and going into the environment. Because if I reset this and then swap them out and put in the resistors, or I could have the resistors already there and just take out the capacitors. So I have to start over again. So right now that's like nothing there. Oh my god, this is going to take a long time. Well, not as much, because apparently I haven't cleared out everything. I don't know. It's coming up slowly. See, it all depends what's best. I think this is better. Oh, the precharged one capacitors were better. That's it. So for precharging, capacitors are better because there's this surge when you engage it, and then it quickly dissipates if there's a resistor. But if it's capacitors, oh, I see. So it all depends on the situation. Huh. Well, for a cold start, though, resistors would seem to be better. And there is a way to, this is synthesizing electricity, but there is a way to lose it, and that is to make, when you go down and back up again, do it really, really tiny. just a fraction. I think that most of the time helps to destroy or decompose the electricity, while if you make big leaps like I'm doing, it helps you synthesize electricity. I think that's the way it works. And it's mostly a probability thing, so statistically speaking, what I'm saying is true most of the time, and sometimes it isn't on rare occasion. But, and why that is, God only knows. Maybe because electricity is essentially a wild stallion at heart, and we may want it to be controlled, but ultimately it will always be wild to some degree, no matter how much we try to contain it and control it and confine it and put it in a bottle and shake it up and make make something out of it that we think might be dependable. It'll always surprise us. So we want to reduce that kind of thing as much as possible so we don't have big surprises too often, but they do happen. We are playing with fire. There's no question about it. All right, so what do we got? 14 amps? No, 1 amp. Now I'm looking at the capacitor. Yeah, I don't think I need to scope the capacitor anymore. Yeah, I may take that out. It's a distraction. I'm looking at the wrong... Because I'm looking at it's lit up in blue because it's highlighted because I'm editing it, but that's not what my target. My target is the inductor. So I'm up to 27 amps now. So now I'll go down to milli, which is a little because I'm nearing my target. Whoopsie. See? That time I didn't come up as high. But I'll just stick with this, maybe because the circuit's trying to make an adjustment to my new way of doing things. Oh my god, I have too much voltage. No, this time I wasn't so lucky. Oy vey, I got 530.5 volts on my inductors and 170 amps. Wow. Oh, it might be because I didn't have caps here because I have resistors. See, so it all depends what you want. If you want more voltage, then go ahead and put caps here, or excuse me, resistors. So the caps work actually better. So I don't have to change anything. I'll leave the caps in place. Yeah, this voltage is too high, and that's what I was testing for to see what would happen. Now in the capacitor, the voltage is lower than it was before. No, not actually. It was low actually too. In fact, it's the same level. So the only thing that's different between the capacitor and the inductor is the amperage. The amperage is quite higher on the capacitor. But the voltage is the same. So I've got nanowatts here, which is better than what it was before at milliwatts, but look at the cost here. I have too much voltage going on here. So that's not my ideal, so I'll leave it the way it is. So the only question I have now is I got to be able to make a different link here to make it be realistic simulator rather than the other simulator by default. And that's unfortunate. So I'm going to have... No, that's not. I'm just going to put them side by side, and I'll move this over to make room and to center it, and I'll have 2 links instead of 1. And then people will be able to compare the difference. I'll have to think of a better... statement than this, though. Something that would gravitate you towards the ideal. An ideal paradox, I don't know. So anyway, I don't have anything more to say. Okay, so that's it then.